quick presentation today. We want to talk a little bit about power transformers and specifically how to optimize or reduce costs, optimize the design, and improve supply chain. So three main things we want to talk about today, kind of three components. First one is being the use of milled radial spacers in your winding, transitioning from a raw board with the surface of the screen pattern intact to a milled strip. Second one is calendered crepe conductor wrap. So utilizing that in your conductor. And then finally, using low density pressboard barriers in placement of high density. So as we start to look into them individually, milled radial spacers. The key point here is that we are removing the screen pattern from the board. So we can see on the left, this is a board as it's produced off of our pre-compressed machine in St. Johnsbury, Vermont. And then on the right is a milled strip where we are removing both top and bottom surface of those strips during the production process. Four main benefits to doing this. The first one is the reduced thickness variation. So here is we're only talking about tolerances, board tolerances versus a milled strip. On a board tolerance is plus or minus 5%, IEEE spec plus or minus 5%. However, on a milled spacer tolerance, we have a plus or minus 0.064 millimeter. So this is allowing for a more precise and more consistent winding height for your process. The second key point is the moisture adjustment, is where during the production process of these milled strips, we are actually adjusting for the actual moisture content of that board at the time. And I'll go into a little more detail in a minute. The third one is the edges of these milled strips are radiused, so we don't have a sharp corner on those edges. We put a bevel on there in order to eliminate any risk of damaging that conductor wrap during the process. And lastly is the improved compressibility characteristics of a milled strip. Again, by removing that screen pattern, you get some advantages. So to look at some examples of each of these four main benefits. The first one with the reduced thickness tolerance. If we have a winding that we have 200 3mm spacers, if we take the board tolerance, again, of plus or minus 5%, that gives you a total possible error of 30mm in your stack height. So when you think about sizing windings at the end of your process, everything's within spec, you could have to adjust up to 30mm. However, with the milled spacer tolerance, again, with that 200 3mm spacers, that gets reduced down to the 12.8mm. So a significant improvement on that. To take it one step further, through the process control and the production of these spacers, we know that about 97% of the spacers are within 0.03mm of that specified thickness. Again, further reducing the total tolerance or potential error in that winding height. So really reducing the amount of adjustments or sizing you have to do. So then moving on to moisture adjustment. So here, as I said, is we are taking the moisture content at the time of production and knowing that as it dries, it's going to shrink or it's going to change during the drying process. So to give an example, if we desire a nominal thickness of 1.5mm as that spacer is dried, so when we produce it, we know that moisture content is actually 5%. So based on our curve, our shrinkage curve, we know that's going to shrink approximately 3.2%. So we actually mill that strip thicker than the 1.5, almost 1.55, to allow and compensate for that moisture shrinkage during the process. So that gives you, after dry out, your final desired thickness of 1.5mm. As I mentioned before, the edge radius, or the edges of these spacers are radiused. So an example on the right, this is just a piece of board cut to the same dimensions. You can see sharp kind of corners here, non-broken edges, higher risk of damaging a conductor wrap during pressing. Whereas on the radial strips, the milled strips, we have this nice radius here to eliminate that risk. And lastly is the improved compressibility characteristics. So by removing that screen pattern on either side, you decrease your compressibility of those spacers, you increase the reversible compressibility, so how much it springs back after that pressure is removed, and you get much more consistent compressibility characteristics across various spacer thicknesses. So a couple charts at the bottom. On the left, you can see these are three spacer thicknesses with very consistent compressibility properties, between 3 and 4%, consistent across all. However, if you go to the unmilled, this is with the screen pattern intact, compressibility is much higher, which is okay, you can compensate for that in your process. However, it's much different depending on the spacer that you use. So if you have a thicker spacer, you have less overall screen pattern, less compressibility. Same thing is true on the reversible side. You can see the milled spacers with that screen pattern removed. You have higher reversible, more of that is compressed, comes back when the pressure is removed, and consistent across your various spacer thicknesses. Whereas on with the screen pattern intact, again, it's variable, less of it comes back, more inconsistencies in the process or in the product. So moving on from there to the second is the calendered crepe conductor insulation. So as we know, with conductor insulation, the key thing to look at is the required high dielectric strength of that material. And really, on a winding or on a conductor, that's determined by the thickness of the paper and the number of layers that you use. However, when you put that into a winding, your turn-to-turn thickness between those two conductors is really, or can be optimized by wrapping that paper as tightly as possible around that conductor. And that requires high tension on those wrapping machines. So as you wrap this conductor, you pull it tighter, you get much more thinner and much more consistent thickness on those materials. So in order to do this, that requires high strength on your conductor wrap. And really, when you consider the strength of the paper, that requires two factors. One is the actual tensile strength of the paper and also the elongation. So the best conductor wrap that you can use will have a high tensile strength and also a high elongation. So looking at different types of conductor insulation that can be used, you have first your non-crepe, your traditional flat papers. Can be used as a conductor wrap. You see our elongation here, 2 to 4%. Then we get into what's known as a calendered crepe. That you get, it's crepe paper, goes through a calendering process. So you reduce your thickness, that gets you a higher elongation, which can also be used on winding conductor. And lastly, you have your standard crepes, uncalendered crepes. And in these, your elongation can vary quite a bit. Shown here, 50 to 200%. And really that's used leads and cables, hand wrapping applications, things like that. So a couple things with the different conductors that we have. Winding conductors are consistent. It's the same size. It's wrapped in a consistent manner, machine wrapped. And then you have your leads and cables, whereas really where you see the traditional crepe paper, they're flexible. They can have odd shapes. You're trying to hand wrap over connections, crimps, things like that. And those are either machine or hand wrapped. So now we want to focus on this calendered crepe conductor. So you can see here again, we have that 8 to 12% elongation, quite a bit higher than our traditional non-crepe flat papers. So within Weidmann, we have 22 HCC. You might also hear it called Denison crepe. You might also hear it called calendered crepe. All these different things. This is again a calendered crepe product where it's flat paper is creped and then goes through a calendering where we get that is densified and you get much more consistent thickness and a reduced thickness of that paper. So what this allows us to do is you can achieve a thickness tolerance of flat paper, much more consistent thickness, but you also get the strength of a crepe paper with that higher elongation, really allowing the wrapping machines to wrap this conductor, pull higher tension, wind faster, give you more consistent and optimize in your space factor within your winding. So the last thing we want to talk about is the use of low density pressboard barriers. So here we start to look at the relative permittivity of these barriers. And really that is relating the effect of the material on the capacitance to air. So we always want to reference back to air as a permittivity of 1. Transformer oil is around 2.2, and then we have, if theoretically, pure cellulose is around 6. So when we put all those things together, we have cellulose material of different densities impregnated with your liquid, and that will give you the relative permittivity between 3.8 and 4.6. And that is depending on the materials used, really dependent on density. Density will affect how much oil is absorbed into that material, which will ultimately affect your relative permittivity. Bringing that into the design of a transformer, specifically we focus a lot on the high load space or face-to-face, but in this case, really break it down as simple as possible with two materials, the transformer oil and the solid material, which is impregnated by that oil. Simply by changing your high density material, again with a relative permittivity of 4.6, exchange that with a low density with that lower value of 3.8, what that does is it shifts the stress within those two materials. So shifting more of that stress into the board and out of the oil. The oil is predominantly your weaker component. So the more you can shift out of that oil into the board, the better. So in this example specifically, by exchanging those materials, we get a reduction of stress in the liquid by about 6%. So when we look at that and what the impact of that is in a transformer and a design, we come back to the Weidmann reference curves. So we have our different curves here. Using insulation dielectric analysis, we can see the impact of these changes and what that means in the overall kind of integrity or the strength of the design. So as the relative permittivities are exchanged between those different liquids, you see a shift, again, out of the oil into the pressboard and ultimately changing the percent margin or the margin in those gaps to see more optimized designs. So as an example in this, so we have the same design system, again, looking predominantly in the high to low space. So we have two coils here with 3 barriers between. And in this case, we are exchanging from T4 barriers high density to a low density, high val barrier, shifting that relative permittivity down closer to the oil where that stress is changed. And focusing in on the uniform area between those gaps, we can see a change in the percent margin. And it's tough to see on here, but in this case, with the T4 barriers, we have a percent margin of -1%. So actually the stress on that one of these areas drops below the strength based on the Weidmann reference curves. Simply by exchanging those barriers, we see an increase from -1 to a +2%. So we're able to shift that stress into the board, reduce that in the oil, and ultimately bring that percent margin to a better level. And this process is usually an iterative process. You'll make an exchange, you'll do an analysis, you'll see the impact, you'll make a change. We could possibly reduce your high-low, we could change your gap spacing, all that sort of stuff. Going back to the 3 things we talked about, the milled radial strips, to get your improved thickness tolerance, your improved compressibility properties, your conductor wrap, the use of Calendered crepe conductor wrap to get a better space factor in your winding. And then finally, the ability to exchange your pressboard barriers from a high density, higher permittivity to a lower density, lower permittivity value to improve your design. Our team here, mainly in the Vermont location, the engineers really utilize these 3 tools and many others to help optimize the installation design of different systems. So with that, I'll open it up if you guys have any questions.
Would you say the 5% plus minus 5%, is that more of a unit to unit concern or literally like a bay to bay concern?
I'd say it could be either, because I mean, I'd say we're typically within better than plus or minus 5%. However, you could have more variation in if those spacers came from different lots of board. So you could see.
That's fairly likely. That's ultimately what I'm asking.
Yeah.
You can have multiple batches in a given piece.
Exactly. I think we have the traceability to know where it comes from, but we can't guarantee that all of the key spacers, thousands of them that go into a winding, came from the same batch. They likely don't. So that's where you could see more variation, like coil to coil, as opposed to the milled, where they're adjusted and compensated for that.